Sveiki, mano vardas Gintarė Karolina Džiugaitė. Šiandien pristatysiu vieną iš savo darbo pagrindinių krypčių, kur tyrinėju mašininio mokymo modelių generalizaciją. Šiandien daugiau šnekėsiu apie teorinę savo darbo pusę, bet taip pat dirbu su empiriniais metodais. Taip pat norėjau padėkoti organizatoriams už kvietimą pristatyti savo darbą. Šnekėsiu angliškai, kad būtų lengviau terminus išversti, kad nereikėtų lietuvių kalbą versti. Okay, let me start. So to start with, I'll give a quick introduction into machine learning theory. In machine learning, we're giving some training data. It might be pairs of inputs and outputs, X and Ys. So for example, in maybe image classification setting, we might have X's which are input images and Ys that are labels of the images. The first assumption we're going to make is the following. So we'll assume that the labels are produced by some function h star. Now, this assumption can actually be relaxed, so it's not really necessary, but to start with, for the crash course, we'll focus on this assumption. So we might want to identify h star from our training data. Now, of course, it's not usually possible to identify h star from the training data. And in fact, in machine learning, we usually care about testing the classifier we obtain or the predictor we obtain, not on the training data itself, but we want it to work well on future unseen data, so-called test data. So the next assumption we'll make is the following. Past training data and future test data are independent and identically distributed from some unknown distribution D. So we'll assume it's very often, there's an assumption made very often that the training data and the test data are ID and coming from the same data distribution. And we'll modify the goal to be the following. So we'll be choosing a predictor h hat such that it misclassifies an input X with low probability for any data point sampled from our data distribution. This induces a very natural definition of risk, which is the probability of misclassification. And it will be denoted by R with the subscript D, where D represents a data distribution, and we're testing the classifier H. So to kind of circle back, we would like then to choose a classifier H hat, which has small risk, right? So we might look for a minimizer or the risk. Of course, there's a problem. The data distribution is unknown, so we don't actually have access to the risk itself. What we do instead of machine learning is we use the training data S that we are given already. And we perform empirical risk minimization. So we choose h hat that minimizes the empirical risk. So it minimizes the errors made on the training set. So h hat is an empirical risk minimizer now of our error. Now, does this make sense? Well, it does. It has some really nice properties. So for example, the expected empirical risk for a fixed classifier H equals risk. So that is the empirical risk is an unbiased estimate of risk. So here I just copied down the definition of the empirical risk minimization again, and kind of copied the side that empirical risk is an unbiased estimate of risk, which is very nice, but there was a problem. So assume that the data distribution is continuous, and all we care about really for this example is that no two examples are equal. And consider the following kind of silly classifier, h hat, noted by this map from memorization, that predicts the correct label in the example is in the training set, but predicts the opposite label if the example comes from a test set. It's unknown. Now, of course, implementing such a predictor is not really even maybe possible, because then you would essentially know h star, but just for this, to illustrate the problem, let's assume that we can. Then the empirical risk, all this classifier h hat that memorizes the training data is 0, right? Because it perfectly predicts on the training data. But its risk, indicated by this RD of this classifier, is 1. It's the worst possible. So there is no generalization. H hat does not generalize at all, right? Because it's perfectly predicted on the training data, but it's very poor job predicting on the test set on new and seen examples, which is a problem. There is a solution. So instead, we could consider relying on some inductive biases of the algorithm. For example, we might be picking a restricted class of classifiers that we are minimizing over So for example, instead of considering any size neural network, we might consider a depth-1 neural network, and so on, and considering simpler predictors. Or maybe we can add an explicit regularizer. So for example, instead of just minimizing the error, we also penalize for some kind of notion of complexity of our predictor, the hypothesis H. So here is again the empirical risk minimization, which just minimizes the risk itself. Now, the natural question that rises is, can we characterize this difference between the risk and empirical risk? So, which we refer to as generalization error or generalization gap. Okay. To do so, I'll be introducing a growth function. So first, consider all labelings that can be achieved by predictors in our hypothesis class. So for example, consider inputs x1 to xm, and let h of x1 to xm denote all possible labelings that hypothesis in your hypothesis class can produce on this set of examples. Then the growth function is maximizing over any inputs the number of labelings you can achieve. So the growth function is 2 to the m. Then it's a problem, right? Because the hypothesis in our hypothesis class can actually achieve any sort of labeling on the training set of size m, potentially, right? Which is problematic from kind of binding this gap between the generalization, binding the generalization error gap between risk and empirical risk. In fact, there is this theorem stating that the growth function takes one of the following forms. So it's either 2 to the m, or it's of the order m to the d, which is much slower. And the d here, so a class H with polynomial growth, so m to the d growth, is a VC class with VC dimension d. So basically, the number of possible labelings is not growing too fast with the size of our training set. Then you can think about it as the hypothesis space having limited complexity and its VC dimension being smaller, where d represents the growth. And this actually turns out to be very useful for binding the generalization error. So if H is a VC class of dimension d, so characterizing the growth of this growth function, and our training set S is of size m, then we can say that the worst generalization error for any hypothesis uniformly in our hypothesis class in expectation is bounded by an order of square root of d, which is VC dimension divided by n. So we can uniformly bound the generalization error for any hypothesis in our hypothesis class, and this hypothesis class has a small VC dimension. Let me introduce a couple more useful decompositions that allow us to think about generalization error and kind of complexity about hypothesis class. So here's one of them. The risk can be decomposed into the following two terms, and this is really a trivial decomposition where just we have this nth term, which is the best risk that can be achieved by the hypothesis in our class. And we are adding and subtracting the same term just to have this decomposition. The first term, which is the best class achieved by predictors in our hypothesis class, is called the approximation error. And the second term, which is the difference between the predictor we are evaluating and the performance of the risk of the predictor that is the best in the class, is called the estimation error. And there are natural trade-offs between the two. So for example, as we increase the size of our hypothesis class H, in general, the approximation error, of course, will be going down because we'll have more and more predictors to choose from. And eventually we'll have a predictor that fits the data even better. But on the same time, the estimation error will be going up. So it will be harder and harder to choose kind of the right predictor. On the other hand, if we decrease the hypothesis class, so if we consider smaller hypothesis classes, then of course our approximation error will be going up as we have like fewer and fewer predictors to choose from, but the estimation error will be going down. So maybe the learning problem will be getting easier. Here's another decomposition. So again, risk of the classifier H hat can be decomposed into the following two terms. Again, this decomposition is really trivial. We're just adding and subtracting the empirical risk term here. The first term is empirical risk, right? We can right away just evaluate it on our training set. And the second term is the generalization error, which is this difference between risk and empirical risk. Now, in general, we can uniform bounds try to bound the generalization error uniformly over all hypotheses in the hypothesis class H. So they're looking to bound the worst case error for any predictors in our class. So for example, as we just saw on the previous slide, if we have a VC class of small VC dimension, we can bound this worst case generalization error in terms of VC dimension of our hypothesis class divided by n and some other terms. This is after rescalings. And this bound holds with high probability over the training set samples. So here is the illustration of kind of these different trade-offs. So as the complexity of our hypothesis class H increases, the training error usually decreases, right? Because we have more and more predictors or more complex predictors, whatever notions of complexity you're thinking about, to fit our training data. So the training error, of course, will be going down. But the test error, it initially goes down and goes up. And this is really because of these trade-offs that the risk can be decomposed in terms of approximation error plus estimation error. And we know that as we increase the complexity, while one is going down, the other one is going up. So it will not be decreasing or increasing monotonically. Now, do these, when it comes to explaining generalization, we can ask kind of what role theory plays in explaining generalization in deep learning, for example. So let H hat be a neural network predictor learned by stochastic gradient descent. So essentially trying to mimic empirical risk minimization. And we can, again, try to kind of get these generalization guarantees, right? So we can try to bound the risk, maybe with high probability in terms of empirical risk plus some other term, right? That maybe bounds the error uniformly. And this other term can depend on many things, like hypothesis class, as we saw, maybe depends just on the VC dimension. It can depend on the number of samples we have, the probability of failure of the bounded data distribution, as is the training data itself, the algorithm we use, and maybe the actual classifier H hat that we got, the actual neural network that we got. The fewer terms this bound depends on, the more general the theory. So the VC theory that we saw on the slide in a couple of slides ago, it only depends on the hypothesis class, the number of samples we have, and probability of failure of the bound. So let's consider a simple neural network, let's say with one hidden layer. For neural networks, the VC dimension is roughly lower bounded by the number of parameters. Okay, so MNIST, the data set, which is image classification data set, I should mention, has 784 input dimensions. Okay, so each X is in, it takes 784 dimensions. And let's say we have one hidden layer with 600 units in that layer. So we have more actually than 470 parameters, 70,000 parameters, sorry, which is a lot larger than the number of training data we have in MNIST data set, which is only 55,000. Okay, so VC dimension is essentially larger than, it's almost like 500,000 or larger. And M here is only 55,000. If you look at the ratio between the two, the ratio, of course, will be massive, right? So for the amount of data we have, the VC complexity, VC dimension is really large. The complexity of the hypothesis class of just this tiny neural network that no one really uses in practice anymore is very large. So if we look back at this or look at a different type of graph, where on the x-axis we have the number of training points, and on the y-axis we have the generalization error. Of course, one could argue that, let's say VC theory, as the number of data increases, our VC dimension does not change. And so eventually we'll get a bound on the generalization error, which is a quantity between 0 and 1, to be below 1. So we'll get a meaningful bound. But that's not what happens in practice. In practice, when we get more training data, we actually increase the size of the neural network. So while we kind of move along on this x-axis, we end up moving also increasing the complexity of the hypothesis class. And we're actually back in this blue regime, where for the complexity of our hypothesis class, the number of data is not sufficient to bring down this bound epsilon to be below 1. And don't forget that we are talking here about error, which is a quantity between 0 and 1. And we're bounding it with a term that's way larger than 1. So what does it really mean to explain? So the fact that the number of parameters in the neural network cannot really kind of capture generalization and bound generalization in a meaningful way has been appreciated long ago. So here's a paper from over 20 years ago by Peter Bartlett saying that the size of the weights is more important than the size of the network. So if we go back to kind of our generalization bounds, it means that the bound depends on some norm of the weights instead of the number of the parameters in the neural network, and some other things like margin. So I will not go into detail. So we can again evaluate these bounds in practical settings, and we will see that as training progresses, which is here this x-axis, so as we take more and more stochastic gradient steps, some kind of norm of the weights is growing, okay, which is worse for the bound. The looser the bound, the higher the norm. But in the bound, the norm is kind of counteracted by the margin. So we're dividing by the margin. And margin is also growing, which is a good sign, right? Because we want margin, if path norm is growing, we want margin to grow even larger. And this is a little hard to see here, but actually the path norm is here on the log axis. So the path norm goes a lot faster than the margin. And when you evaluate these bounds, you'll see that this green curve, which is our generalization bound, so this epsilon, is actually shoots up and is above 1 for the whole training time. So it's not really again yielding meaningful bounds. While the training and test errors, which are overlapping here, are just continuing to decrease, okay? So even these norm-based bounds, which are kind of, thinking about restricting, maybe looking only not at the whole hypothesis class, but only looking at a subset of the hypothesis class with like smaller norm on the weights, and it's not sufficient to uniformly bound the error even over these smaller classes. So to take a step back, kind of the goal of my work is to understand why deep learning works and the limits of when it works. And I'll be mostly kind of trying to explain the following observation. So in deep learning, networks are trained with stochastic gradient descent. So we're just minimizing the risk, the empirical risk, to 0 training error. Okay, so we know that the training error is really small or close to 0. Yet the classical approximation error, estimation error trade-off is missing, at least with respect to the usual notions of complexity, like the VC dimension, other kind of dimensions, number of parameters, whatever, or some norms of the weights. So again, going back to this plot where on the x-axis I had the complexity of the hypothesis class, so complexity, let's say, of a neural network. And on the y-axis I had the error, the training error. We know that as complexity increases, it's decreasing. The test error in this classical kind of approximation estimation error trade-off would be going down and then up, right? As we discussed a few slides back. In this case, we have the complexity is not high enough, and the test error would be really large because we have few predictors, basically very simple maybe predictors to choose from. In this case, we have the complexities maybe large enough to kind of get predictors, but it's a harder learning problem. And maybe a good model would be, looking at this plot would be lying somewhere here. But deep learning actually operates in this totally new regime. So in this regime, as we keep increasing the complexity and the training error is 0 and remains at 0, the test error is actually also going down. So this curve is often referred to as double descent curve, and there are a lot of papers written in the last few years. But this is not what I'll be focusing on. I'll be focusing today on something that was named benign interpolation by Peter Bartlett, just last year actually. And there was a lot of other related work. But this is really trying to understand the generalization of predictors that can interpolate the training data, meaning that they can fit the training data perfectly to 0 error, but still work well on new and seen data. So when there is enough capacity to memorize the training data, but generalization still happens. So can we study generalization and interpolation using standard tools? So again, to kind of return to my introduction slides, the classical approach to controlling generalization error exploits uniform convergence, right? I'll repeat the key idea here. So the risk of the learned model can be decomposed to the empirical risk of the learned model plus the generalization error. And we obtain this just by adding and subtracting some terms, right? It's a trivial decomposition. Empirical risk is something we can just measure, of course, in our training set, so it's nothing we need to estimate or whatever. But the generalization error, we can bound that in the worst case, the worst generalization error of any possible model, any possible predictor in our hypothesis class. And this is what uniform bounds are about, right? Uniformly bounding the error of our hypothesis class. And this approach works very well for small model classes. So for example, classes with small VC dimension. And fully characterizes learnability for such classes, along with the classical bias complexity trade-off or the approximation estimation error trade-off. How do these classical tools work for deep learning? Well, there were several possible versions of this attack that were applied in the past, and they're understood to not explain generalization. So VC dimension, as I mentioned, that worked by Bartlett, trying to use the norms instead of VC dimension. So there are random micro-Bayes bounds for those who know what it is. I won't go into the details, but there are all these different versions, some of which I presented earlier. We also have some work actually from a few years ago trying to bound the generalization error of randomized predictors that were built from the learned predictors and so on. But in all these cases, we keep running into barriers. So actually, we can't really get, numerically typed bounds, or even we can't get the right dependencies of the bounds, as they vary, for example, the architecture size and things like that. So are we missing something? There was a paper from last year that was presented at NeurIPS and got actually the Best Paper Award, named Uniform Convergence may be unable to explain generalization in deep learning. This was work by Nagarajan and Coulter, and it received a lot of attention. So here's the example that they present. They consider the following data distribution. The features are sampled from a union of concentric high-dimensional spheres, and the labels correspond to which sphere a point is on. So in this example, we have the inner sphere and the outer sphere. If you're in the inner sphere, then the label is 1. If the example is on the outer sphere, the label is 0. If you run stochastic gradient descent with the deep neural network, you find a classifier H hat, which has the following decision boundaries illustrated by blue. So as you can see, these are the training points. And very locally, it overfits. So it kind of overcompensates around the training data, but otherwise actually returns a pretty good predictor. In this paper, they showed that there is then an adversarial data set S bar that it has an equal probability under your data distribution as S, for which H hat will have large empirical risk. So the original data set, for example, have a training point here, 0. The adversarial data set will have a data point on the inner sphere instead that has the opposite label. And now because our classifier H hat illustrated by blue was overfitting locally, it will also make mistakes on this adversarial data set as bar. So by symmetry, then there is an adversarial hypothesis, another adversarial hypothesis, which has a large generalization error for the data set, S for the green one. The one we would have learned from if we were learning on the data set as bar. So the key idea is that the existence of this adversarial hypothesis and data set implies that uniform generalization error is vacuously large. And this is actually true not only for this particular sphere example, but you can generalize it to an example where the data distribution satisfies kind of similar properties. So is uniform convergence dead? Well, not quite. In our paper published this year, we show we defend uniform convergence and suggest how to use surrogate classifiers and classes for which uniform convergence holds. So deep learning conjecture proposed by Nagarajan and Coulter is the following. Stochastic gradient descent finds a fit that is simple at a macroscopic level, leading to good generalization, but also has many of these microscopic fluctuations, so it locally refits, which hurts uniform convergence. That work doesn't really show us how, if true, this can be exploited in the analysis of generalization error. What we do in our paper is we demonstrate that one may exploit uniform convergence when the conjecture is true. We construct a de-randomized version of the predictor that still matches the predictor at the macroscopic level, so it kind of has a very similar structure and therefore has good generalization. But if you try, of course, to prove the generalization method wouldn't work in the first case, right? But instead, we get rid of the microscopic fluctuations, therefore showing that one can generalize, show generalization, prove generalization using classical uniform convergence approaches. So to give you a little bit more intuition, if as you define this classifier H hat, which is in blue, that locally overfits, we might be constructing a surrogate classifier, maybe G hat, and this is just an illustration, that's not exactly what we do, that maybe smooths out around those overfitting points, but roughly preserves the structure of the classifier. So it has the same generalization, but will also improve, we can also show provably that it will generalize because we got rid of these microscopic fluctuations around training points. So roadblocks arise in using uniform bounds to explain performance of complex models. As I said, when the model is really like, has low complexity, the hypothesis class has low complexity, it's possible to prove generalization. But when we move to more complex models, that uniform convergence, standard uniform convergence approaches are not really useful anymore. We describe a new role that uniform bounds may play in studying interpolating predictors. So these predictors that are powerful enough to memorize the data by the following two steps. So first, we define uniform convergence when the model complexity grows with sample size. We also study generalization of the predictor H hat in terms of a de-randomized version, so a surrogate predictor, designing the surrogate to live in a class with uniform convergence, and the combined uniform convergence of the surrogate and then the approximation error to explain the performance of our original classifier H hat. And we apply this to explain generalization in over-parameterized linear regression. So when the number of dimensions is much larger than the number of training points. So we explain also this benign overfitting phenomenon in linear regression. We construct de-randomized surrogates via conditioning for general learning problems. So at the end, I'm not sure I'll have time to actually go for it, but at the very end, I might show how to, kind of a general recipe, how to construct these surrogates. We also explain generalization in Nagarajan culture example setting via models with surrogates constructed by conditioning. So while in their example, they failed to, they show that uniform convergence cannot be used to get generalization guarantees for the original class, by constructing the surrogate class, we can actually get provable generalization guarantees via uniform convergence. In model machine learning, as we get more data, we build larger and more complex models. So in classical learning theory, we have this hypothesis class. And if we have 100 data points, we still minimize our empirical risk over this hypothesis class. If we had 1,000 data points, we still use the same hypothesis class. If we had 1,000,000, still remain in the same hypothesis class. Right? That's why I was saying that, as you get more data, eventually your bounds will go to 0. But modern practice is different. If I have 100 data points, we'll use this hypothesis class H. If we get 1,000 data points, we'll use a more complex hypothesis class H2. If we get 1,000,000 data points, we'll expand our hypothesis even more, right? So as I was mentioning earlier with deep learning, for example, as we get more and more data, we might be considering larger and larger neural networks. So previous work does not provide a notion of uniform convergence when available complexity grows with sample size. So in uniform convergence approaches, you don't allow the complexity to grow. So for example, you consider the same hypothesis with fixed VC dimension, sorry. So first, let me introduce this new notion of structural Glovenko-Cantelli classes. So focus on uniform convergence for sequences of problems with varying complexity, just like I showed in the image before. So for example, here on the x-axis, we have the sample size. On the y-axis, we have the generalization error. And for the model we have, the generalization error might be decreasing with sample size. The training error, on the other hand, of course, will probably be increasing and eventually converging to risk, right? When we get more data, we consider this different model class, model 2, like in the previous picture, that might be more complex, that will be shifted to the right. So again, as the sample size increases, it will eventually go to 0. The training error, on the other hand, will plateau somewhere lower, right? Because we have more complexity now, and we can fit more training data to small training error, and so on. As we increase the complexity, we're decreasing the training error eventually for the same size. And these red lines kind of illustrate the modern practice. So as we increase the training set size from N1 to N2 to N3, we'll be also increasing the model classes we consider, right? And the generalization error will actually be dropping down, the training error as well. We say that a hypothesis class H has the Glovenko-Cantelli property with respect to distribution D, if and only if the worst case generalization error goes to 0 as we increase the size of the training set, right? So this is kind of the standard uniform convergence notion. Now, instead, we define a sequence of hypothesis classes indexed by P. And we say that this sequence of hypothesis classes has a structural Glovenko-Cantelli property with respect to maybe a sequence of data distributions D, if and only if the worst case generalization error, the expectation of it goes to 0 as we increase the index of the sequence, right? So kind of like in the picture just beforehand, we don't only consider like a single model and how its generalization error goes to 0, but we consider the sequence of model 1, model 2, model 3, and we want the generalization error to eventually converge to 0. So when we say uniform convergence fails for a sequence of learning problems, we mean that the sequence does not have a structural Glovenko-Cantelli property. And this was really kind of loosely handled for machine learning, and there was no notion of the structural Glovenko-Cantelli. There was only uniform convergence, right? People ignore the fact that as you get more data, you increase the complexity. This is a type of failure exhibited in the example by Nagraj and Coulter, actually. We want to relate the generalization error for problems where structural Glovenko-Cantelli fails to the ones where it holds. The new problem we introduce is called the surrogate. We do this by partitioning the generalization error of our classifier H hat that we learned into parts for the error from the approximation by the surrogate. Okay, so how different the surrogate is from H hat, and also the generalization error of the surrogate. So now we can separately consider how close our surrogate is to the initial classifier, and whether we can get a generalization guarantee for the surrogate. Let G be a second hypothesis class to which we can extend the loss function L. Okay. So for any surrogate learned by, for any surrogate learned hypothesis G hat in our surrogate class G, we can write down the following decomposition. So again, this is a really trivial decomposition, but it will be useful for understanding what role uniform convergence can play for interpolated predictors. So here we have the expected generalization error of our original classifier H hat, and we can decompose it into the following. We can decompose it into the difference in risks between H hat and G hat, so original classifier and the surrogate, the generalization error of G hat, the generalization error of the surrogate, and also the empirical risk differences between the original classifier and the surrogate. So you can think of G hat as de-randomized version of H hat. Globally, G hat should look like H hat, but locally it should smooth where H hat was overfitting to the data. So returning to this example, you can think about H hat, the original classifiers, fitting all the training points microscopically, all the around M, but G hat is smoothing out. If we de-randomize enough, G hat may belong to a class with uniform convergence, right? So the more de-randomization we do, the kind of the less we are fitting to the training set we have, and it will probably be easier to show uniform convergence. If we de-randomize too much, G hat may not have similar risk and empirical risk with H hat, right? They might not look anything similar. And if you look back at this decomposition, the generalization error of H hat not only depends on the generalization error of the surrogate, but also between these risk differences between the surrogate and the original classifier. So this creates a tension which we must balance, right? So we need to de-randomize just enough to get something useful where uniform convergence holds, but we're also not too far from where we started. So let me apply kind of all this to studying over-parameterized linear regression. So this is really building on the work by Bartlett, Long, Lugosi, and Siegler that was published just a year ago. Consider just standard linear regression setting where the response y is a linear function of x with some, and x is a Gaussian design matrix with some noise added. The dimensionality d is much larger than the number of training points. We have n. We'll consider square loss functions. The learning algorithm learns a minimum norm empirical risk minimizer, which is this b hat, and it can be written down analytically. And here's a theorem from Bartlett et al. Paper. When the sequence of design covariance matrices is benign, and benign is defined in their paper, our minimum norm empirical risk minimizer has risk converging to the base risk as the number of training points go to infinity. Okay, so we'll generalize. We show that while this minimum norm interpolator has good generalization, that one cannot get good generalization using uniform convergence, good generalization bounds. So any sequence, even data-dependent sequences of hypothesis classes containing minimum norm solution, minimum norm empirical risk minimizer, with high probability cannot be structural Gulbenko-Quintelli. So we need to, one would maybe think that, okay, in this case, is uniform convergence a useful way to bound the generalization error of interpolated predictors? Well, now we can use our approach as I presented in the previous slide using surrogate classes. So just kind of to recap, the good performance of b hat, this minimum norm empirical risk minimizer, demonstrated by Bartlett et al., cannot be explained by uniform convergence of a class containing b hat. So now I'll be kind of taking the approach or relating the approach in Bartlett et al. Paper, how they prove generalization, to the surrogate analysis that we have. So in Bartlett et al. Paper, they write down a bias variance decomposition for this linear predictor of the expected risk of b hat. And we show that this decomposition is the same in expectation as a surrogate decomposition with a surrogate that fits data with large response noise. So before I was talking about H hat and G hat. In our case, we'll be talking about H hat, which is B hat in linear regression, and the surrogate will be this minimum norm empirical risk minimizer that is learning on the noiseless data. So there's no epsilon added to the response variables. And what this does is actually the surrogate then is constrained to a well-behaved compact set. So instead of having predictors like all over the place, will be by considering the surrogate that learns on the noiseless data, we're actually considering only predictors that belong to this compact set. So here's a correspondence between the terms that appear in Bartlett et al. Analysis and our surrogate analysis. The bias term in their analysis corresponds to the generalization error of the surrogate in our decomposition, and the variance term in their analysis is the risk difference between the surrogate and our original classifier. So the risk difference between B hat and B hat 0. The irreducible error in Bartlett analysis then corresponds to the excess empirical risk term, so the third term in our decomposition. And here's the result that we get. So the sequence of induced surrogate hypothesis classes is structural Gulbenko-Quintelli if the following norm, so the predictor that we learned projected on the covariance matrix of the features goes to 0. The surrogate predictor B hat naught learned on the noiseless data belongs to a class with uniform convergence, or that has structural Glavenko-Contelli properties, so this upgraded version of uniform convergence. Then we can combine this generalization error of the surrogate with the bounds that appear in Bartlett paper on the difference between the surrogate and the original classifier to get a generalization guarantee using uniform convergence on the predictor beta hat. So we saw that a surrogate can be useful in improving our understanding of a learning task, but the example of a surrogate based on Bartlett et al. Paper was bespoke to that task. So of course, the natural question arises, are there general recipes to find surrogates without relying on the structure of a particular task? And the answer is yes. So we show in our paper that via randomized predictors and probabilistic conditioning, we can construct surrogate classifiers, surrogate classes more generally. So let M1 of H be the space of probability distributions over H. So you can think about it as, maybe a distribution over the parameters of a neural network. The average risk of the randomized classifier, so kind of similar as before, is now the expected risk of any classifier sampled from Q. So a similar definition can be extended to empirical risk, right? We're just averaging empirical risk over samples from our randomized predictors. We'll be using G to denote a surrogate hypothesis class, which is randomized again. The loss function, we assume that the loss function just extends to this space of probability distributions. Again, by we integrate the loss over predictors H sampled from Q. So the risk function of on the space of probability measures induced by this extension of loss matches the average risk. So since de-randomized surrogates can be useful, as in the case of linear regression, how might we construct them for a generic classifier H hat? Here's one way to do it. So in Bartlett's example, we could have redrawn the response noise instead of nullifying it. So instead of learning a surrogate predictor on the noiseless data, we can learn a surrogate predictor beta hat prime, where we resample fresh noise independently from the noise in our training set. Now notice that beta hat and the surrogate beta hat prime have a common conditional distribution given the x's. So the key insight is to use this conditional distribution as a surrogate, as our randomized surrogate. So this conditional distribution can be considered as a randomized predictor that redraws the predictor beta hat prime from this conditional distribution for each test instance. So if I have a test example and I want to make a prediction on it, first I will sample fresh noise epsilon prime, learn the predictor beta hat prime, and then make a prediction. More generally, for any learned hypothesis H hat and any signal field F, Q, which is this conditional distribution, conditioning on the sigma field, is a surrogate that is coupled with H hat only through the sigma field. Now, what's nice about using this as a surrogate predictor is that the difference between the risk of H hat and the risk of this randomized predictor Q in expectation equals to 0. So in expectation, they had the same risk. So going back to our decomposition of the risk of the classifier H hat, we are now left with only two terms if we choose our surrogate classifier to be this conditional distribution. So since the difference in the risks vanishes, we are only left with the expected difference between of the empirical risks between Q and H hat, and also the generalization error of Q. If H hat overfits, we expect this conditional distribution, our surrogate classifier, to have higher empirical risk because we are, of course, fitting close to the data, but lower generalization error. So it should be easier to get better, tighter uniform convergence bounds on this last term. And there are many ways to de-randomize, to choose our sigma field, right? So on one extreme, we might have a trivial sigma field. On another extreme, we might have a full sigma field. So on a trivial sigma field, we might be de-randomizing everything and essentially resampling the whole training set, in which, of course, the generalization error of such a classifier will be 0. So there is no term left here. And we're only left to explain the difference between empirical risk of Q and H hat, but actually the empirical risk of Q is the risk of Q. So we're kind of back to square one to explaining generalization error of H hat. So it's not very useful. On another extreme, on this full sigma field, if we don't do any de-randomization, our randomized predictor will be conditioning on everything, including like the noise that that was learned and stuff, and we'll just have a direct measure on our original classifier H hat. So in this case, the difference between the empirical risks between Q and H hat is 0 because it's essentially the same predictor, but the generalization error again is no easier to prove. We are left again with proving generalization error of our original classifier H hat instead of some easier to prove surrogate. But of course, there's a lot in between. And some of it is actually very useful. So in this illustration, as we condition on more and more things, we have increasing generalization error, but we have decreasing empirical risk. Here I had a few examples of different sigma fields. So the full sigma field, I talked about the trivial sigma field, but maybe I have like some different examples where I can maybe just redraw some of the features from my training set, or maybe redraw the features given the responses for all examples and refit the model again. Or maybe I redraw only a subset of the training data and construct a randomized predictor in that way. For any given learning problem, some of these will be useful, more useful than others. And we use this approach actually to prove generalization of a classifier in the Lagrangian culture example using uniform convergence on a surrogate class that randomly redraws some of the features. So to conclude, the roadblocks arise in using uniform bounds to explain performance of complex models. A new role that uniform bounds play is by de-randomization and surrogates. The key idea is to relate the learned model to a de-randomized surrogate model. Surrogate may belong to a structural Gouvenko-Quintali class, even when the original classifier H hat doesn't. Surrogates can be constructed via conditioning for generic problems. And there are two examples where uniform convergence fails for the learned model. So for example, one based on the overparameterized linear regression that I talked about, or the one that I just didn't really have time to go through is based on the Lagrangian culture example. A de-randomized surrogate improved our understanding of learning problems in both examples. So that's it. Dar kartą ačiū už kvietimą pristatyti savo darbą ir lauksiu jūsų klausimų, būsiu prisijungusi ir labai norėčiau su jumis visais pašnekėti. Ačiū.
Sveiki, ačiū, labai įdomus pristatymas. Aš nelabai supratau, kas yra tas de-randomization ir kuo tai padeda su to adversarial example. Aš tiesiog trumpai paieškojau, tai tokį radau apibrėžimą, kad vos ne tiesiog yra tos atsitiktinio skaičiaus generatoriaus fiksavimas, kad visą laiką tą pačią seką duoda. Bet pagal šitą apibrėžimą aš nematau, kaip tai galėtų padėti. Ar čia kažkaip tai su regularizacija susiję?
Nieko prieš, jei angliškai atsakysiu.
Taip, prašau.
Ačiū. Yeah, so the term de-randomization itself, we actually introduced it. So it has not been introduced in the past in this context. I'm sure de-randomization means a lot of other things. In back-based bounds, for example, it means a totally different thing. So the way we use de-randomization is the following. So first of all, we want to explain generalization of a predictor that we found with our algorithm. Okay, so it's not a predictor that we arrived at after regularization. It's not a predictor that we arrived at in other ways. It's really, we have a predictor and we want to explain generalization of this particular predictor. And standard approaches would be via uniform convergence, right? So you would show that this predictor belongs maybe to a larger class, and any classifier in that class has good generalization. But this, kind of as I argued in the beginning, it doesn't really work. So the way we propose to address it is kind of find a somewhat related predictor, which we called a de-randomized classifier. And the reason why we call it de-randomized classifier is because we kind of try not to memorize as much of the data, essentially, the way we propose to deal it. Anyway, so you find this predictor that's related to your original predictor, a surrogate predictor, a de-randomized predictor, and you explain generalization for this predictor, plus the gap between the two. Does that make sense? Kind of. So I think the key, so when it comes, for example, to regularization, right? De-randomized predictor, I mean, in some sense, it could be, in some special cases at least, it could be seen as a regularized version of the original predictor, of which, like, generalization properties you're trying to understand. Okay, so it can be related to regularization, kind of indirectly. Though the ways we propose to de-randomize are slightly different. It's like, if you think about, all the information you can get from your training data and the classifier learning all of this information, you're looking for a related classifier that maybe learned less of your training data. Does that kind of roughly make sense? Yeah, and how it's related to adversarial examples. So it's not a standard notion of adversarial examples. In Nagarajan and Coulter paper that I mentioned earlier in the talk, adversarial data set is not like a standard, adversarial example stuff in machine learning, but it's really this data set that's constructed such that your predictor has great generalization, great training error on the data it was learning on, but terrible training error on this adversarial data set.
Okay, thanks. I guess we'll have to look more into the papers to understand the details anyway.
Okay.
Yeah, please. Okay, aš tai turiu du klausimus, bet gal, pirmas tai būtų, ten pačiai, aišku, labai fainas pranešimas, tai, kaip sakant, mano klausimus nežiūrėkit piktai, nors jie gal pasirodys pikti. Man pirmas klausimas buvo, tai šitągi dėl to klasės H, nes kai aš suprantu, ta sudėtingumo klasė, kur mes apsibrėžiam, kokia yra mūsų hipotezė erdvė, jeigu mes imam paprastas klasifikacijos uždavinius, tai ta klasė turėtų būti, aš turiu dvi klasės, tai va, viskas, 2. O jūs, kaip sakant, po to paaiškėja slaiduose, kad sudėtingumo klasė yra konvolucinio, neuroninio tinklo parametrų skaičius. Tai toks gaunasi kaip ir kontrastas. Parametrų skaičius neturėtų būti, jeigu aš noriu išlearnint katę, ar matau katę paveiksliuką ar ne, aš naudosiu sudėtingą konvolucinį tinklą, bet man bus tik 2 klasės. Tai kur čia šuo pakastas?
Yeah, so, aš atsiprašau, bet man bus lengviau atsakyti angliškai.
Kokių problemų?
Aš tiesiog terminą nežinau. So it actually, the complexity of the hypothesis space, the predictors, doesn't necessarily depend on the number of parameters. In fact, when it depends on the number of parameters, it's actually not very useful in deep learning. On the other hand, it also does not depend on the number of classes. So the fact that you're predicting the cat versus dog, for example, it's a binary prediction problem, which gives you kind of access to a lot of the theory out there, but it doesn't define the complexity of your class. Okay, so the complexity of the class is like all the predictors that you can have. So, even if you're predicting, for example, you have like all cats here in your space, all dogs here, maybe it's enough to have a linear threshold, and this would be a simple class if you're classifying with linear thresholds. But if your predictor is really powerful, what prevents it from learning like decision boundary that looks like all kind of like this, right? So this is what kind of you care to understand when you define notions of complexity. VC dimension does depend on the number of parameters. And the reason why I talked about VC dimension is just because it's a very classical approach. And actually, as I explained in the beginning of the talk, is that even 20 years ago, people have recognized that VC dimension is actually not a good notion of complexity when it comes to, for example, deep learning. So it's well known that it cannot explain generalization in deep learning because of the number of parameters. And kind of the key beyond that is that even if you look at different notions of complexity, for example, instead of the number of parameters, you might look at the norms of the parameters. For example, maybe an L2 norm of the parameters. And you can, for example, get generalization bounds that tell you the smaller the L2 norm, the tighter the generalization. But even such things actually cannot explain generalization in deep learning. And this is what kind of part of what Nagarajan and Culture paper showed and what has been kind of already known before and understood, but no one wrote it down basically. So the key is that we really need to go beyond these classical approaches and to develop theory that doesn't study worst case guarantees. But yeah, number of parameters in deep learning definitely will not explain anything. Geras klausimas.
More questions? Daugiau klausimų? Juozai?
Thank you, Gintarė. Excellent talk. Really, really nice to get back to foundations of machine learning. So my question, I think I have a couple of questions. So one is, you really nicely did a really crash course into all these generalization bounds and VC Rademacher complexity type concentration inequality bounds, and even though it's really elegant and nice sort of probabilistic theory of models like SVMs or various kernel-based methods, it's still not very useful in practice, right? And people don't, if they train an SVM or if they use some kernel-based method, they don't look at the bounds to use it in practice, whether it's a good model, or can I use this fitted model in practice or not? Do you expect, and this theory almost kind of, I don't know, maybe, of course you know this much better, but it's kind of now developed, and maybe people don't expect a lot more practically useful results. And do you expect that somehow more useful theory is possible for these deep learning-like models? You mentioned an example of a linear regression. So do you think that's possible, that a theory which is based on the concepts and ideas you are developing could potentially be useful practically and not be just another elegant theory?
Yeah, that's a great and tough question. So I'm not entirely sure. So I would like actually to say something. You mentioned that you think that a lot of the theory has been developed and maybe there's not much further we can go, but actually there is. So even a few years ago, people have not been talking about the double descent curve, right? Where as you increase the complexity, your generalization error goes down, but then it goes up, right? But as you increase it further, it actually goes down again, or multiple descent. As it sounds like you're familiar with the literature, so I'll just not go into too much detail. But so that's, I think, an example where a lot of the kind of theory that's being developed now is trying to explain these multiple descent phenomena. And more generally, I think while there is a lot of theory and nice theory for understanding that low complexity regime, such as Rademacher complexities, as you mentioned, right? There's covering bounds and stuff, but not enough yet theory to explain over-parameterized complex regimes where data distribution matters. So I think a lot of kind of more data dependence will be coming into the bounds, and that's a lot of my work is on that. regarding whether it can be useful or whether it will ever replace held outside bounds, I'm not sure. I think data-dependent bounds might, and if we manage to kind of describe what nice data distributions are, for example, image data, right, in classification, in vision. But otherwise, yeah, I'm not really sure. Right? We have these two extremes, like VC theory, and we have another extreme where we have held outside bounds that obviously can tell you specifically for this case what the bound is, right, up to Monte Carlo error. And the further we go from this held outside bound, of course, the more explanatory power we get, right? We understand more generally kind of why these classifiers generalize, but of course we lose precision. So I think there will always be this trade-off between how tight the bound is and how explanatory it is.
Thanks a lot. And maybe if I may ask one more question.
Yeah.
So for me, and correct me if I'm wrong, the theory that you're trying to build is somehow a theory of stochastic gradient descent and growing models. Because in the previous, in this generation of classical, proving these bounds for classical generalization models like classical models like SVMs, it's as you mentioned, these are essentially on the complexity of the expressivity of the hypothesis class, and now it's about trying to kind of capture this elusive stochastic gradient descent, and as this model complexity grows with the number of parameters. So the more, and it's as you illustrated, there's so much to distill with just a linear regression and trying to do SGD on growing linear regression models. And once we do that, do you think we can get to more complex architectures once we understand linear regression, or that's maybe this is more like kind of a view, but suppose we get done and we understand, or your research helps us understand linear regression very well and how SGD performs, and so how we go to CNNs and various other architectures.
Yeah, so I think there is still a massive gap, of course, between linear regression and like a deep network. But I do think it helps us kind of appreciate the complexity of the problem. So even in linear regression, right, over-parameterized linear regression, as we can see, there is a lot of theory to develop, and there is a lot unknown and unexplained. On the other hand, when you, for example, look at implicit regularization results, right, when you move from, let's say, linear models to maybe factorized linear models, you can show that actually in some cases, in a simple case, like linear regression, stochastic gradient descent does implicit regularization, like it minimizes, let's say, L2 norm or something, right? But as you move to more complex models, even as you said, like, factorized linear models or like deep linear networks, for example, in some cases, there is no regularizer in terms of the norm, right? So a lot changes as you change the architectures. And I think, this probably will be the case for generalization theory as well. The theory, kind of this de-randomization theory I presented today, it's very general. So it's really independent of the structure of the hypothesis space itself. But of course, to apply it, you need to take the structure probably into account. And, it's complicated, right? There are a lot of too many unknowns. Yeah, so maybe I kind of diverged from your original question. You might need to remind me. But yeah, I think there is still a huge step between, linear models and deep networks, but we still need to understand the simpler structures first.
Thank you. Yep. Fully agree.